Hey everyone, welcome to the second part of the video. So in the previous part, we talked about specifically osmolarity, and we got a little bit into how it can differ from tonicity. So just as a quick refresher, real quick point that I just wanted to touch on before we get into it for tonicity. We do need to remember one thing, and that is that osmolarity is a measure of total solute concentration regardless of whether that solute is impermeable or permeable. Sorry for the mouthful there, but this sentence is really important when it comes to understanding what differentiates osmolarity and tonicity. So osmolarity is telling us about the total solute concentration, right? Tonicity, on the other hand, when we talk about tonicity is telling us which direction water will move based on non-permeable or impermeable, for the sake of consistency, impermeable solutes. All right, so this is what's differentiating tonicity and osmolarity. So for those of you who are better visual learners, it's important for us to sort of maybe draw this out, look at it in a diagram, and see exactly what this looks like. So in my opinion, best way to do this is just to draw a diagram of a cell. So sorry for the page break here, but so we'll call this our cell. And then we'll make this little boundary here. Okay. So what we're going to say is that the black circle here is our cell, and we're going to assume that anything that's contained within here is the ECF. So this is going to be our extracellular fluid. So this is a sort of like a little picture into what a cell would look like when it's going around in the body. So how do we talk about osmolarity and how do we talk about tonicity? Well, remember that osmolarity is the total solute concentration, and we know that we're talking about only non-permeable solutes when it comes to tonicity. So what does that look like in practice? Well, let's start off by putting some solutes in our cell, right? So let's say we're going to add some of these, right? Actually, let me make it easier and actually count them up. So I'm going to add 5 of these green ones, right? And we're going to say green, let's make that our sodium ions, all right? And then we're going to have brown, and we're going to make that 5, same thing. And in this case, we'll call this urea. And if you watch the previous video, you know that sodium, it's impermeable, right? It's a non-permeable solute. It cannot cross the membrane without some type of a transport channel, whereas the converse is true for urea, right? Urea can just passively diffuse across the membranes, no issues there whatsoever. So we've got 5 molecules urea, 5 molecules sodium inside our cell. Let's say we have 3 molecules of urea outside of the cell in the extracellular fluid, and 7 molecules of sodium in the extracellular fluid. Now, first things first, let's calculate the osmolarity, right? And determine whether the solution is hyperosmotic, hypoosmotic, or isoosmotic with the cell. Or excuse me, the other way around, whether the cell is hyperosmotic, isoosmotic, or hypoosmotic to the extracellular environment. So in order for us to determine this, we need to first calculate the osmolarity, right? So we know that osmolarity is the total non-permeable and impermeable. So I'm going to highlight and use orange for non-permeable. And I'm going to make this, I'm going to use orange for permeable. I'm going to use yellow for non-permeable. All right. And then in this case, we'll add up our Na. So on the inside the cell, we have 5 Na plus, okay? And then we've got 5 urea. That's going to give us a total osmolarity of 10 osmolar. So 10 osmolar inside the cell, right? Outside the cell, we've got 7 this time molecules, 7 molecules of sodium, plus our additional 3 molecules of urea. Now, we calculate our osmolarity. That's going to be, again, non-permeable, and then permeable. We're adding both of those, and that again gives us 10 osmolar. So we've got 10 osmolar inside. Oops, that looks like 100, sorry. 10 osmolar inside, 10 osmolar outside. 10 osmolar outside. So that is going to mean that we have equal osmolarities inside and outside the cell. So the correct sentence here to define this would be, the cell is iso-osmotic with the ECF. Now, if the cell's osmolarity was greater than the extracellular environment, it would be hyperosmotic, and if it was less than the extracellular environment, it would be hypoosmotic. So that tells us about osmolarity. So just from a purely osmolarity basis, right? If we're assuming that this barrier, like the barrier that's the cell, right? The cell's membrane. If we're assuming that nothing gets through it, right? The only thing gets through it is water, we're not going to see any net movement of water, right? Because there's an equal osmolarity on either side. However, this is where the all-important concept of tonicity comes into play. So remember, like I said earlier, tonicity only takes into account the non-permeable solutes, right? So when we're taking into account the non-permeable solutes, we're going to forget about urea in our equation. We're forgetting all about urea, right? Oh, that was weird. Sorry about that. Not sure why I didn't erase. There we go. Okay. So we're forgetting about urea. When we have urea, or when we only have sodium, what we now find is that in the ECF, we have a concentration of 7 Na plus, and in the in the intracellular fluid, we have 5 sodium, right? It's 5 sodium. Now, when we're talking about non-permeable solutes, this is where the hypertonic, hypotonic, isotonic comes into play. Hypotonic means, and remember, this is all relative. So if we're talking about the cell, we're saying the cell with respect to the extracellular environment, right? So in this case, if we're talking about the cell, if the cell is hypotonic to the extracellular environment, that means that there is a lower concentration, right? Hypotonic equals lower concentration of non-permeable solutes compared to environment. Oh God, it's a horrible spelling. Environment. Hypertonic is essentially that in the complete opposite, right? So boom. And then we just do a little switch. We have increased concentration of non-permeable solids compared to environment. And I'm sure, as you can guess, that leaves us with our isotonic, which is going to be equal. Oops, sorry for that equal sign. Right? So these are our 3 statements. Compared to the environment, we're always talking about it in comparison to the environment. Now, based off of that, in this case, this is like your Bio 1 type of an example. Inside the cell, we have 5, quantities, 5 units of non-permeable solute. And then the outside, we have 7, which means that the ICF is less than the ECF. And if we go back to our statements, well, which one does this match with? Hypotonic, right? So the cell is hypotonic to the environment. Now, remember I said tonicity tells us what direction water is going to move in based off non-permeable solutes, right? The only solutes that really have an effect in which direction, and this is really important, if you get anything from the video, it should be this. If we have, and I can write this as well, if we have any solutes So, sorry, one more time. Only solutes that are non-permeable affect water movement, right? That's really crucial. So in this case, in order to reach equilibrium, we're going to have water move from its low concentration, which is here, to high concentration, which is here, which means consequently the cell is going to get bigger, right? Because water is rushing in. All right, so that sort of brings us to the end of this sort of two-part video series. Hopefully that was helpful and helps cleans up any of the concepts or loose ends that some of you guys may have. If you didn't find the video helpful, still need more supplementary, or you need maybe more supplementary review, I strongly recommend going on to Khan Academy's MCAT resources, specifically in their homeostasis unit, going over those videos, and I'll link those in the Canvas page as well. And also looking over the Osmolarity and Tonicity primer that Dr. R posted for the lecture as well. So thanks everyone, and good luck on the exam.